Welcome back to SCA Academy. In the last class, we have discussed about Unit 1 important points from PGTRB Chemistry Unit 1. In this class, we will discuss about important points from Unit 2. These points are much more useful for the examination point of view. Those who want, they can make use of this. I will discuss about the important points from Unit 2. The first point, structural isomerism. There are four different kinds of structural isomerism: ionization isomerism, hydrate isomerism, and coordination isomerism, and linkage isomerism. These things we will discuss one by one, and also stereoisomerism. These are all the stereoisomers. We have two types of stereoisomers: geometrical isomers and optical isomers. So we can expect questions based on this. At least two questions we can expect from this point. This unit 2 is a very easy unit. If we practice properly, we can get around 8 to 9 marks easily, but we can expect around 10 questions from this unit for the examination. But if you study properly, we can score at least 9 marks easily from this unit. Now the next point, and now we'll discuss about the ionization isomer. The first isomer, the structural isomer. They have the same molecular formula, or the chemical formula, complex formula, and different ions in solutions. When you dissolve a complex in a solvent like water or any other solvent, these molecules will give different ions, but they have the same molecular formula. Molecular formula is same, but different ions. Here in the first complex, SO4 minus ion is, and this complex cation is produced. But they have the same molecular formula, but Br minus and the different complex cation is produced. So this type of isomerism is called ionization isomers. They will produce different ions in solutions. Next one, hydrate isomerism. Isomers, in the hydrate isomers differs in the number of water molecules present as ligands. Now look at the complex CrCl3H2O thrice. Here there are 3 water molecules are here as ligands. The second, the chloride is reduced, it goes out of the ligand cage, and 4 hydrated ligands are there. In the third one, there are 5 hydrated ligands are there, but the coordination number is 6, but the complex is different. This type of isomerism is called hydrate isomers. Now the next one, fifth one, coordination isomerism. The interchange of ligands. These are the different complexes. In a single complex, each cation and anion is also a complex ions. In a single complex, if we take a single complex, the cation part is also a complex and anion part is also a complex. They will interchange the ions as ligands. They will interchange their ligands and produce the different complex. So this is the cation part and this is the anion part. They will interchange their ligands and produce a different complex. The interchange of ligands between the cationic and anionic part present in the complex produces this kind of isomerism. So this is called the coordination isomerism. Next one, a linkage isomerism. We can expect question based on this. Have the same molecular formula. All the isomers have the same molecular formula, but different in the mode of attachment here. Here's ligands NO2 minus. So this kind, if nitrogen is attached to the central metal atom, they are called as nitroligands. If oxygen is attached to the central atom, they are called the nitrative ligands. From the type of attachment, we can separate these isomers. This isomer is called linkage isomers. So these are the easy ones. We can also expect questions based on this when they ask questions very easily. Next one, these are the geometrical isomerism. And the other type, stereoisomers, geometrical isomers. We can expect cis-trans isomerism from the point of view of geometrical isomers. If you take the coordination number 4, there are two types, tetrahedral and square planar complexes are there. If you take the coordination complex, here I am giving only important points related to the examination point of view. So these are the very important ones. When you take the coordination number 4, tetrahedral and square planar complexes are there. Generally, tetrahedral molecules will not give any isomers. Why? Because all the ligands are in adjacent position to each other. In tetrahedral molecules are the 4 ligands adjacent to each other, so they will not produce any geometrical isomerism. But it can also produce geometrical isomerism only in some special cases, not in all cases. Now, the geometrical isomerism in the others. Now we'll go to the square planar complexes. This is square planar complexes. Already we have seen tetrahedral, they will not produce any geometrical isomers. When you come to square planar complexes of the type MA4, if the ligands are of the same type MA4, all are the same type, they will not give any isomer or only one isomer, only one type of isomer. Generally, it will not give any isomer. And if you take isomer of this Ma3B, here also they can give only one isomer. You will not get any other different isomers. If you take Ma2B2, there are two isomers are there, cis and trans isomers. If you take all the 4 isomer ligands are different, you'll get 3 isomers. We can also expect questions based on this. And if you take the ligands as bidentate ligand, like MAB twice, you'll get 2 isomers. Examples: MPTCl2, C2H5 thrice. This is twice. Okay, sorry. This is twice. Okay, and 2 times. This is the, it will create 2 isomers. Now we'll go to the next one. Geometrical isomerism, the coordination number 6. This is also a different type of in the octahedral complexes. Ma5B will get only one isomers. Then Ma4B2 will get 2 isomers are possible in this kind. 4 A types, one type of isomer, one type of ligands, and 2 other type of ligands will get 2 isomers. We can expect questions based on this. Now, this part is very important. We can expect question based on this. Merorizomous and factional. Mer means meridional, fac means facial. Ma3B3, if you have some kind of ligands and B other kind of ligands, 2 kinds of ligands of different types. If 3 same ligands are in the same equatorial plane of the octahedron, they will create merorizomers. If all the 3 isomers are the same equatorial position, they are called the merorizomers. Facisomer means they are in the face of the triangular face of the octahedron. If all the 3 same type are in the triangular face, if they are in the triangular face, they will become fachisomers or facial isomers. Example, like here when you look at this, rhodium Cl3, pyridine 3, they exist as fac and meroisomers. In the fac isomers, all the pyridine and all the chlorines are in the same phase. This is like a phase of the octahedron. They will present in the single phase of the octahedron. On the other way, they will be in the other phase. Meridional means they are in the trans. Otherwise, we can call it as trans. Because pyridine and pyridine are in the trans, here it is cis. They will be in the equatorial positions. Look at this, Cl, Cl, Cl. They are in the equatorial positions. So this type will give the meridional isomers. If they are in the same phase, they will give the facial isomers. Okay, now we'll go to the next point. Octahedral complexes with bidentate ligands, MAA2X2. It can exist as cis-trans isomers. We have seen a lot of examples based on this. And octahedral complexes of the type, this is one different one, M, A, B, C, D, E, F. All the ligands are all different. So we can expect around 15 isomers from this type. and only one complex is possible from this type of complex. Example, I'll go to the next one. Thermodynamic stability. Stability is the different one. There are two kinds of stabilities: thermodynamic stabilities and kinetic stabilities. Thermodynamic stabilities measures the extent to which the complex will be formed, how extent the complex will be formed or will be formed into another species when the system has reached equilibrium. This measures the thermodynamic stability of the complex. And kinetic stability, it refers to the speed with which the transformation leading to the equilibrium will occur. How fast the equilibrium will occur. This shows the kinetic stability. So general difference between the kinetic stability and thermodynamic stability. The stability of coordination complexes are measured in a stepwise stability constants. This is based on the Bajrang methods. There are two methods are there. One of the method is the Bajrang method. A formation constant, stepwise formation constant. If we multiply all the stepwise formation constant, we will get the stability constants of the particular complex. Stepwise stability constant values decreases with the successive replacement of the ligands. When add the successive ligands to the metals, the stability constant value keep on decreases. Next one, stability of the complex of the metals follows the Irving-Williams series. The stability also based on the Irving-Williams series. Next one, low spin complexes with the D3 and D6. They have the spherical d orbitals D3 and D6, and high spin complexes the D3, D5 and D8 are inert complexes. Because in D3 and D6, in the low spin complexes, the T2G orbitals is either filled or half filled. So they are stable. But in the case of high spin complexes, D3, D5 and D8 are half filled, either filled or half filled. So they are inert complexes. Next one, all others are the low spin complexes. All others are the labile complexes. I'll go to the orbitals optical activity of the complexes. This part is very important. The previous part we can expect around one or two questions from the previous part. From this point, the unit 2 is very important. We can score around 8 marks easily from this point of syllabus, this part of the syllabus, the optical activity. First we have to, when you take a single carbon, we have to assign the priority to all the groups attached to each carbons from the high priority to low priority. So to give priority, we have to follow the CIP rules. In the CIP rules, we have to give priority for the groups which have the more atomic number element. We have to give them more atomic number. The element which have more atomic number, we have to give high priority. And the element with the low atomic number, we have to give low priority. If it is a clockwise direction, clockwise sequence, when it raise from high priority to low priority, it is R configurations. If it is anti-clockwise sequence, it is S configurations. This is very important when you take as a single carbon. Now, this is the Fisher projection. There are different kinds of projections. We will see all of them one by one. First, we will discuss about the Fisher projection. In the Fisher projection, numbering of the carbons, generally numbering will be given in the carbons. If it is not given, we have to start from top of the carbon, top carbon to the bottom carbon. Generally, top carbon should be given number 1 and the bottom carbon should be given at the end. Priority of the groups to be assigned for all the groups attached to all asymmetric carbons. We have to give the priority for asymmetric carbons and give priority based on the CIP, Chon-Ingold-Prolog system. The element with the more atomic number should be given more priority. This we have discussed already. The element with the atomic number, more atomic number should have more priority. Like this, we have to give the priority. Now, we go to the next one. Yes, it's like this. The pressure projection is like this. The groups in the horizontal position are above the plane. The groups in the horizontal positions are above the plane or towards the viewer. And the groups in the vertical positions are below the plane or away from the viewer. They are away from the viewer. So the least priority group should be in the vertical position. If it is in the vertical positions, we can assign the number directly, or otherwise we have to invert the position, invert the configuration. Now the next one, trace the priority from high priority to the low priority. This is how to assign in the Fisher projection, whether it is R configuration or S configurations. Trace the priority from high priority to the low priority. The low priority group is in the horizontal. The lowest priority group is in the horizontal position. Like here, this is the vertical position. It is below the plane or away from the viewer. And this is the horizontal position. This is the horizontal position. It is towards the viewer or above the paper. Like this, we have to view the Fisher projection. Now, the priority groups, trace the priority from high priority to lower priority. The low priority group is in the horizontal position. If it is in the horizontal position, the clockwise tracing gives S configurations. We have to keep it in our mind. The lowest priority group, that is the fourth priority group, is in the horizontal position. Clockwise tracing gives the S configurations, and the anti-clockwise tracing will give the R configuration. The next one, the lowest priority group is in the vertical position. If it is in the vertical position, the clockwise tracing gives the R configurations and the anti-clockwise tracing gives the S configuration. If it is anti-clockwise tracing from the high priority to lower priority, we have to give S configurations. Now, if you take an example of this, find the R and S configurations of the molecule. This is the questions have been asked there, PGTIB 2014. So I have given here. This is the molecule like this. We have to give number from this carbon 1, 2, 3 and 4. Here the least priority, bromine has the highest atomic number, so we have to assign number 1 for this. And the next carbon and chlorine is attached to this carbon, so we have to give number 2 for this. And methyl group has the number 3 and hydrogen has the number 4. Here the least priority hydrogen is in the horizontal position, so the clockwise direction, clockwise rotation, clockwise tracing of the groups 1, this is the priority number 1, this priority number 2 and this priority number 3. The clockwise tracing for when a least priority group is in the horizontal positions, so the clockwise tracing of the second carbon gives S configuration. In the third carbon, this is the first carbon and this is the second carbon, asymmetric carbon is in the second position and in the third position. For the third carbon, here also the least priority group is in the horizontal position, so numbering should be 1 for the chlorine. First priority should be given for chlorine and the second priority we have to give for this carbon because bromine is attached to here, and the third is the methyl group. So this is also following the clockwise direction and this will also give the S configurations because the least priority group is in the horizontal position. Okay, now we'll go to the next one. Okay, so far we have discussed around 24 points from the unit 2. The next class we will discuss some very important points, how to convert Fisher projection to other forms like Sahas and Newman projections, and how to assign the configurations. This point is very important, and what are the stable conformations we'll discuss in the next class. So those points I'll give in the next class. Those who are interested, we are giving test materials and mock test for PGTRB. Those who are interested, they can take part. So thank you so much for watching this session. Thank you.